All right. So in the last class, we looked at. So in the last class, we looked at a meaning and application of Newton's law. We look at how we can identify forces on bodies. We also looked at resultant force and acceleration. We looked at inertia and how mass affects acceleration. So today we're going to focus on conservation of momentum and impulse and momentum calculations. So that is what our classes will tilt towards this morning. All right. So that said, let's get started. And I hope that we solved questions on what we did the last time, because I told us to check out questions on that and check out questions on that and work on it. Right. And I hope that we actually did that, because that's the path to mastery. That's how you master whatever thing that has been taught. Right. We have to make that a habit, the habit of solving past questions. That'll be really, really fine. All right. Someone raised the hand. What's the problem? Abasi. Okay. Now let's look at momentum. Sorry, I need to charge this headset. All right. Confirm you can hear me, please. Can you confirm you can hear me with a thumbs up? All right. So now we're looking at momentum. All right, welcome. Titi, how are you doing? Mesa, how are you doing? Um, again is on the call. Paul, how are you doing? Hope you are good. And hope we are studying. Welcome, guys. All right. All right. So what are the key things about momentum, right? So momentum is simply the quantity of motion possessed by a body, right? It as well tells you how difficult it is to stop a moving object. And it's something that is dependent on two key things. It depends on mass and it depends on the velocity of the object. So momentum is simply the quantity of motion possessed by a body. Right. It measures how difficult it is actually to stop a body in motion. All right. And now there are key things I said about momentum. So when you talk about momentum, something should come to our mind, right? So momentum is dependent on two key things. So let's have momentum at the center of what we're doing. And then since it's at the center, sorry, let's have it easier. This way. Let's economize space. So when you have momentum, it depends on two key things. It depends on the mass of the object. So it depends on mass on the object. It also depends on what? On the velocity of the body of the object. All right. So that is what your momentum depends upon, right? So anytime you hear about momentum, those two things come to your mind. The mass of the body should come to your mind and the velocity of the body as well. should come to your mind. So two key variables that we should pay attention to. All right. So that said, let's give a few examples for us to actually understand something about momentum as regarding an object, right? So since momentum is a function of mass and velocity, one could as well highlight that momentum, mathematically, you have that momentum is equal to your mass, like we did yesterday, times velocity. In symbol, we can say that P is equal to what? mv, right? So remember that m is the mass of the body, v is the velocity of the body. Now, based on this formula, there are a few things that we'll have to take note of when it comes to momentum. Sorry. So when it comes to momentum, there are a few things I want us to take note of. So everybody, please take note of that, right? Sometimes questions can come in that regard. Now, what is that thing I want us to know? Let's assume we have a particular body or a particular object, right, that has a little, that the mass is small, right? The mass of an object might be small, but if the speed is much, right, the body might end up having more, what do you call it? Having more momentum, right? So it all depends on that. Now, there's something I want to say that a heavy object moving slowly, right, may have the same momentum as a light object that is moving what? Very fast. So it's a function of both the mass and the velocity. I might be moving very slow, right? But if my mass is quite heavy, it's going to cover up for me. I'm going to have a very good momentum. Sometimes it's also possible that an object that might have a very small mass, but because of the speed is very high, it will have the same momentum as a heavy object that is moving slowly, but have a very big mass. You understand? So I think you get my point. You understand what I'm trying to say about momentum regarding the how it depends on mass and velocity. Can you give me a thumbs up if you actually get all those grammar I'm trying to speak right here? A thumbs up if you do, guys. A thumbs up if you do. All right. Um, this is my equation one. I'm just trying to box this equation. I don't know why it's refusing to box. So this is my equation one. All right. So that said, I highlighted something very key, right? That we should note that a heavy object, because it's a function of mass and velocity, a heavy object that is moving slowly may have this person is not in class today. That name I like so much, Nikki Gold. They have the same momentum as a light object. Yes, as a light object moving fast. All right, beautiful. So you can solve this thing mathematically, right? You can have an object that has a very big mass but a very small momentum. Can we try that? Let's look at an example and see what happens right here. Right. Let's say we have an object. Yes, boss. It's linear momentum. Yeah. Now let's have an object. Let's say that example now. Let me use people in the class. Let's say that Titi now, that her mass, let's say she has a weight of let's say 50, which Titi looks like someone that is very slim from her voice. Am I correct? Yeah, yeah, from your voice, yeah. So let's give her 45 kg.
No, I'm 50.
Okay. So let's give her 50 kg. Okay. Mm. Um, Now let's look at who again is on the call. Let's use, okay, you called Paul. Let me now use you. Now let's use Chinonso, right? So Chinonso on the call. They don't even know how to spell your name again. So Chinonso on the call. That guy eats a lot. So I think he eats a lot. So we should give him up to like 70 kg. Now let's give Titi. Titi might know how to run. So let's give her a speed of, let's say, uh, 1000 meter per second. But I doubt if she can do this. Hey, you're giving me a thumbs up. Now let's say Chinon. So because of how heavy he might be, right? Let's say he just travels as 20. Let's say, let me just give him 50 to have mercy on him, since he's a guy as well, 50 meter per second. So now let's calculate the momentum for the both of them, right? So you understand what I'm trying to say. Now, for the momentum now, what would the momentum look like? So for Titi now, right? For Titi at this point, we're going to do mass times velocity. So her momentum, right? Let's say use our P will be equal to what? 50 times 1,000. So that momentum for TT is equal to what? That is 50000. That's 50,000, right? Are we there? And the unit of momentum actually is kg. Sorry, I forgot to say that. Meter per second. That's the unit of momentum, kg meter per second. So I think I should actually reduce this here, right? And then put that it is measured in kg meter per second, right? So let's have it this way. All right. So that said, let's go to Chinonso now that it's a lot. That's Emmanuel is answering Chinonso on the call, right? So let's have Chinonso right here. And I want us to be very fast today because my stomach is singing national anthem. So we have the momentum right here equal to 70 multiplied by 50. Well, this class, you guys are not trying. Nobody comes to the class with lunch. At least somebody should be coming to class with something now. So that as I teach, you can just give me then that kind of thing. But nobody does that. You guys will just log in. Some persons are even walking on the road and they are joining. Nobody comes to class with anything. Eh? That's not fair. So now 7 times 5 is 35. So that's around. Am I correct? Come and eat rice. Chai. Chai. So you are eating and learning. Is online class not interesting? Hmm? Can you imagine someone is eating and the person is learning, right? That's quite beautiful. That's quite beautiful. Because I can remember back in the days, there was this teacher we had back then, right? This woman will tell you to, I think I was in primary school back then. So when she gets you eating something, she will collect the thing from you. It doesn't end there. She will throw it away and she'll be like, oh, yeah, say bye bye to it. You'll be waving your hands for like 5 minutes, waving your hands. So my anger then is why, you've actually collected this. So why telling me to wave? Children, how they can be now. I will be waving to my food or my sweet and the rest of them. So, but here you are at home, comfortably learning and eating at the same time. So I think online class is a very good one. Just that the person teaching cannot eat. That's the only punishment. It's in two ways. So imagine I want to eat gari now. Which hand will I use to write? But I have soup already on my hands now. You get the point now. All right. So this is kg meter per second. Right. So can you see something now? What can you see there? We could see something quite interesting, that there is a difference in their momentum, right? There's a difference in their momentum. And what brought about the difference in momentum is very clear. In as much as Emmanuel had more weight, right? Or more mass rather, he was weighing 1,000, but because his speed was not good enough, you could see that Titi had that very advantage of moving. Titi had the advantage of moving past him. Can you see that? So that's the basis upon your of which your momentum works, right? So we've established that concept, and we're still going to come back to this very concept. So please take notes as we journey together. All right. Sorry. Now, let's look at something quite interesting, which is the law of conservation of momentum. But before then, I think I should touch your impulse like I did yesterday. Very quick one. Let's touch impulse a bit and see the connections. And Paul, were you to get the questions I asked you to get the last time? Did you do that? Paul?
I've gotten some. I'll send them to the group.
Okay, that's interesting. Well done, brother. If it is Emmanuel I gave that task, he will drop like 15 minutes voice note why he didn't get the passwords. But I'm glad he delivered. Okay, I think we've highlighted key things. Okay. Yeah, just send them to the group. I think it will make sense as we are learning, we are solving those questions immediately. Is that okay?
Yes, sir.
All right. I don't see I finished. Some days I like that. All right. So I've established these key things. And another thing I want you to know is that momentum is a vector quantity, right? Momentum is a vector quantity. So know this. Let me quickly introduce this. Momentum is a vector quantity. Momentum is a vector quantity. When I mean it's a vector quantity, right, it will mean that it has magnitude and it has direction, right? And that said, there are key things you need to know about this because it's a vector quantity. If two objects move in opposite direction, right, that very momenta, which also regardless of your singular now, must carry signs. You have to indicate with the signs. If this one move in the right direction, that is positive. This guy moves in the left direction, that is negative. It is very important when we start handling collision questions. Is that okay? So what am I trying to highlight here? I'm just trying to say that, number one, that if two objects move in opposite direction, if they move in opposite direction, their momenta must carry signs, right? You have to indicate it with signs. They must carry signs because it's a vector quantity. So what does that entail? It's simply saying that the second thing I want you to know, for example, if it's moving in the right direction, it should indicate what? Negative. Sorry, positive rather. So you have to indicate the signs, right? If the object are moving in different direction, because it's momentum, we'll have to take note of that. Because this will really help us when we start solving questions on that collision. So we'll have the left direction. The left direction is negative, right? And why am I saying all of these things, guys? I'm saying this because this becomes very important. Becomes important in collision questions. Justice is not in class. Also, anointed rather is not feeling fine, so people can reach out to him. Okay, Justice, you're here. Oh, interesting. You guys can reach out to anointed and Joseph, right? I'll mention their names on the group, so just do well to check out on them. The other guys in the hospital is as serious as that, so do well to reach out to them and know how they are doing very, very important. I think you know how the stress can be. Yeah, so do well to check up on them. So this becomes very important in collision equations. So the next thing I want us to look at is change in momentum, right? So if velocity changes, momentum will do what? Change. Is that not so? Because momentum is dependent on mass and velocity. Now, the next thing I want you to take note of us is your change in momentum. All these key points are very important. I saw one question that they asked what happens in a circular, what happens to momentum in a circular motion? And that's why I'm writing this statement now. So change in momentum. Now, if velocity changes, momentum will do what? Momentum will change. I hope you guys are writing. You're just watching me. You're watching Nigeria movie. So we'll have change in P is going to be MV minus what? MU. So we can write it as change in P is equal to M open bracket V minus U close bracket. Right. So remember the variables now, as always. But I think I should just write it here for you. So remember that where, right, you have that U is the initial velocity as always. Initial velocity. V is the what? The final velocity. You already know that, what do you call it? That M is the mass of the body. So there's no need adding those ones there. All right. So V is our final velocity. Now, we've linked something from the second law of motion the last time, right? Between impulse and momentum. I linked that the other time. So quickly, let's also bring that in, right, immediately. So I highlighted that the last time, which has to do with your impulse. My friend is not here, Baraka Dauda. Power. Please, somebody should check on her, please. Anybody that have a number, check on Dauda Baraka for me. She's not on the call currently, and that's not a good one. So now, impulse. Please always check up on each other so that we could navigate entirely. I know, sorry, you can't be calling me by this time. Okay, so we have impulse. So impulse is the effect acting over time. All right, so we've established that impulse is equal to force times time. So impulse. The way I've been iterating on this impulse, I believe that when I start solving question, people will be trashing all of everything. That's what I want to see. You know, when I ask you, people start giving me that kind of answer Lillian gave me yesterday. Very powerful answer. All right, so this is my equation number 3.
So I'll send some questions to you.
Okay, I trust you. You deliver like Hebrew women. Have you heard that before? That someone
Yes, sir.
delivers like Hebrew women. Okay, they're a man of God. Susan, the daughter of Abraham. So impulse produces change in momentum. right? So we're going to have that Ft is equal to mv minus mu. Remember where it is coming from, right? From our second law. All right, so let's move to the key thing now, where we're going to get our hands dirty, right, with the key things. So the next one has to do with your conservation of momentum. Conservation of what? Momentum. So now, what's the concept of your conservation of momentum? The concept is simple, right? If there's no external force on the system, if no force is acting on the system, it simply implies that the total momentum remains constant. Total momentum means momentum before, so I'm not feeling well, I feel weak, and I'm having severe headache. Okay, that's your headache. I don't know whether it chooses the days that it happens. I've noticed that it happens on Mondays and on Thursdays. So sorry about that. You'll be fine. So conservation of momentum simply tells you that you have momentum before and momentum after, right? So we're trying to say that when two objects collide together, right? If there's no external force or external thing acting on the system, that the total momentum before collision should be equal to total momentum after, right? That's the conservation of momentum, right? And that concept is coming from the concept of your Newton's third law. Remember your Newton's third law. In Newton's third law, we say that action, right? Action and reaction are equal and opposite. That's the same thing that has to do with momentum, right? Just that way. That thing I explained before. So let's say that during collision, we'll have an object. Object A will push object B. And in turn, object B will push object A, right? Because of what? Your Newton's third law that said for every action, it has what? Equal and opposite reaction. So during collision, object A is going to push B and B is going to push A. There's a very nonsense song that is coming to my head. God forbid. So the forces are equal and opposite, right? So that in which that the momentum gained by one equals the momentum that is lost by the other. So as I push you, you receive, and as well, you push me back as well. So that's based on that the momentum what gained and the momentum lost are equal. So that's the basis upon which we understand our conservation of momentum, right? So this builds on your third law of motion. If you understand what I'm saying, give me a thumbs up, please. Anything also? If you understand what I'm saying, can you give me a thumbs up? Well, Benita, give me a thumbs up. Are you still with me? Titi, you're confused. Lillian, you're confused. Okay, Titi is not confused.
I
It's all
am
right. Lillian is
confused though.
confused. You are confused. Okay. You are confused. Okay. What is confusing you?
I don't really know. Maybe I don't know. Maybe it's just the explanations you are using.
No, is it the 50 kg that is confusing you? Your 50 kg weight.
I know.
All right, so let's go like this again. I said something, that from your Newton's third law, right? We said that every action has equal and opposite reaction. Is that not so? For every action, there is equal and opposite reaction. And we said that conservation of momentum says that total momentum before collision will be equal to total momentum after collision. That is when objects collide, provided there's no external force acting on that system, that momentum is conserved. And I said something. Observe an object. Let's say we have good. Let's use Paul. Let's use Paul and let's use Justice. Let's use the two of them. Now, and they collide together, right? Let's say that I'm coming, you are coming as well. I didn't see you. All those they are Korean movie where this one is coming and they jam and then the other one will help the other one to pick something and the other one will now look the other one and from there, that kind of thing. All right. So Paul but this time I'm using the guys now, so you don't think about any other thing. So Paul will collide with Justice. So what happens there is that Paul pushes Justice and justice as well pushes what? Paul. Is that not so? That's exactly what happens. So the forces are equal and opposite, right? So okay, let's say I'm not moving. Let's say I'm just standing and you hit me. Immediately you hit me, I will respond as well by movement. If I was not moving before and someone hits me, I'm going to move a bit. What does that mean is that momentum he lost in hitting me, I gained it. Do you understand it? Example, another example now. If I slap you, right, I'm losing momentum. So when I release that slap on your face gains that very power. You know, for you to slap someone, it determines on how far you raise your hands up, like on how far you stretch your hand. So as you are stretching that hand and on landing on my face, that momentum you lost, my face is gaining it. It's not lost. Does it make sense now, Titi? Was it still that I was confused before? Good. I know anytime I use slap, you understand. I don't know why. Lillian, do you understand it now? All right, beautiful. So that is what your law of conservation of momentum is trying to say. That if things are colliding, okay, another example now. Let's say we are driving and someone hits us from the back. You know all those drivers that, let's say there's traffic, then the vehicle start moving a bit. The person wants to speed up, you understand? And all of a sudden, the person will hit you guys from the back. When that person hits you guys and your vehicle is not moving, what happens? It jerks everybody forward. What it means is that momentum that was lost by the other vehicle upon colliding with us, we gained it because of that movement that occurred. And that movement that occurred is equal to that momentum that was applied. So momentum is conserved, is not lost. Does that make sense now? Everybody, does it make sense now? All right. Paul and Co. Okay, beautiful. So that's the conservation of momentum, right? It builds upon your Newton's third law, right? So let me put that here for those that are going to read later. So this builds upon your Newton's third law, but I've given an example. So this builds upon the Newton's third law. Nikki Gold Silva, are you following? Okay. Abi went to see David Silva using a lift. This builds upon upon the Newton's third law. Now, if you know you solved questions of what we did last time, can you give me a thumbs up? What we did yesterday? You solved questions after what we did, give me a thumbs up. My God. Yeah, Titi and Co, what are you guys even doing? So after teaching, nobody solves past question.
No, sir. Yeah, I can justify myself. Because
Okay, go
yesterday
ahead and just
I went to greet my grandmother, so like I could not do things.
okay. You went there from
Yes.
2:30 to 3:30. You will greet
No,
her. Wait now.
no,
Wait,
no, I
I'm
wasn't
coming.
there.
Let's know what happened. So now you are trying to tell us that we finished lessons yesterday. All the lessons ended around 2:30. Maybe from when you get there from 3 to 4, you go to her room, you greet her. Then after 30 minutes again, you go to her room again, you greet her, right? And you did that throughout the whole day.
No, that was not what I did.
I want to know. You say you can justify it. You know, you went to your
Yes,
grand.
I
I'm
did.
asking, you went to greet her. Then every five minutes you are greeting her, so that she can
No,
take the
no,
greeting for the next 5 months.
no,
Every morning she withdraws one of them.
no, that's not what happened.
Okay, interesting.
She
You
was
need
in
to
the
be solving these
parlor,
questions. It was
so
what?
we were in the parlor, so I could not leave her there. So I was just there with her and trying to like converse with her, so she'll not feel bored and everything. So she'll feel my
Oh,
presence, sha.
interesting. As a Mike Odo of Who Wants to Be a Millionaire, you were having a conversation with her. Okay, you are doing well. All right, please. There's no time. Use that time. Always okay. What happened that night? You guys continued. Maybe you now took her to cinema. You guys went to watch cinema also to keep her engaged.
No, sir. I told you that I have classes from 7 to 11:30 at night.
So which time will you now use to read? All
I
right.
used to read
So
now
this
when
bit
you wake me up.
okay. This bits upon the Newton's law, third law. This is applicable to every other person on the call that didn't check. Who again is on the call? Because it doesn't make sense. We teaching and teaching. Confidence, you didn't solve past questions. Justice, you have done your ear as if you are not hearing me now. Ferami, you didn't solve any question. Nikki Gold Silver, you didn't solve any question. Okay, Susan says she's not feeling. Ugu Godelaya Abi Gudulia, you didn't solve questions, right? So every morning you guys will join class and talkative will talk and talk, and you put inside your pocket and go. You guys should do better. Okay, talkative. Let me continue. Talking is my work now. I've been busy. Look at what you are saying. Busy doing what? Answer. Good silver.
The whole of yesterday I didn't have chance. I've been busy doing house chores, so I finished around that 8. I had to go to my mommy's shop.
House chores. I'm beginning to wonder. Did you clean? Maybe you guys stay in an estate and you clean the entire house in the whole estate. Can
No,
you imagine what you said?
I washed
How can
the
you do?
two
How can
toilets
you do
and the
house chores from
bedrooms.
2:30 to 12 a.m.?
I had now. We closed
Yeah?
shop around that time. I finished around 8, like I said. I finished around 8. I took my bath, then I went to my mommy's shop. We closed around 10:30. I
God.
still know before I would now. You go try sleep. I've not rested since today.
Somebody said, I know I'm taking this. I'm going to take the next 5 minutes to talk about these things before I start teaching again. Somebody said, she goes to work, she's attending class, and that is an excuse for that person. Kai, oh boy. See, if example now, let me give an example. A very good example you can relate with. Now, let's say that the president has promised you that if you read consistently, like every day after class, if you revise everything that you've done, right? Okay, let me just use myself. Let's say that we have an offer from somebody, and the person said any student that actually solve past questions on everything that you guys have done each day, and that person does it consistently for 3 weeks, that person will receive 5 million. All those excuses you are giving me now, will you hold water? Titi, will you go to your grandma and be entertaining her, cracking joke for her, so to keep her busy? Nikki Good, if we say we have that amount of money, will you still use the whole time, and then will body still be firewood? I'm giving an example, so it boils down to value. It boils down to value, right? It boils down to value. You even told me you took your. Are you calculating the time of bathing as being busy? Will not go kill me for this class, oh. Even if your body is now you are washing a trailer. My goodness, who again is here? Everybody will collect. Paul, you are safe. Sorry, I'm using this is the time that Paul should be learning. I'm using that to do other things. Who again? Confidence. Did you solve questions the last time? Please and please, any topic we treat, try and solve questions. We don't have the whole time in the whole world. I don't know why I'm so concerned as if I'm writing this exam. I don't really know. I can't tell. Maybe because of the love I have for you guys. Hmm? All right, let's continue. So this bit upon Newton's third law, every action has equal and opposite reaction. He that has ears, let him hear, right? What the angel is saying to the church. Value matters a lot. If we attach money to this thing now, you see how you'll be reading. Even as you're walking on the road, you are reading. I know some of you. Nikki Godsave and the rest of them. Equal and opposite reaction. So now, During collision, object A pushes B and object B pushes A as well. So the forces are what? Equal and what? And opposite, right? So momentum gained by one equals momentum gained by the other. So total momentum remains the same. So that means that during collision, let me just put down these key points. You guys are no longer happy with me. Right? During collision, yeah, everybody's not calm. Okay. If you're not happy with me, Abby, that A pushes B an object B pushes A. All right. So see how the way I'm stressing myself. I don't like writing no, but this is what I'm doing so that you guys can still have this note and read. What does it take me to just go straight and solve question and go my way? Right? So the forces are equal and opposite. The forces are equal and opposite. Mhm. So now the law of conservation of momentum says one thing. Mhm. Hence momentum gained by one of them equals the momentum lost by the other. Are we together now? So total momentum remains unchanged. So the law of conservation of momentum, that law simply says that. So the law simply said that if no external force, acts on the system, that what happens? The total momentum remains constant. So mathematically, it simply says that total momentum before collision equal to total momentum after collision. So what do we call this? We call it the law of what? Conservation of mass. This is the law of conservation of mass. Sorry, law of conservation of momentum. Now, mathematically, mathematically, are you there? Mathematically, a thumbs up if you're with me. Mathematically, this thing means that you have two formulas. The first one, yeah, thumbs up. Benita, a thumbs up. Are you with me, Benita, at all? Sorry, Benita, after now, can you message me, please? Let me know your progress so far. So, yeah, message me, Benita, after the class. Let me know your progress so far. So, total momentum before collision. I think we should have a prize gift, though. Anybody that can get up to 300 should have a 30K. What do you think? What do we think, guys? Should we do that? Can we make it a deal? I'm glad this call is recorded. Justice, you're giving me a thumbs down. How much will be good, Justice? Just say it on the call. Justice, how much will be good? Say it on the call. I'm glad it's recorded as an evidence. Can we do 300 and above? Jambis April. 300 and above. Let's make it a 30K. We have a deal. 300 and above, a 30K. Yeah, it's sealed. The call is recorded and we can always come back to it. Justice, is it okay? Justice. Why is Justice laughing? It's too small.
No, nothing.
Justice, it's too small, but
It's not the price amount, it's the score.
it's the score. It's too high. All right. So total momentum. What if everyone gets above 300? I'm not scared. You're talking about Sismo here. What are you saying? Which we know is not possible. I'm being realistic, actually. I'm being realistic. But let's assume that everybody gets that. It does around 300. How much? Yeah, but let's assume it's possible. We agree it's possible anyway. But then let's work towards that. Not be by what if it is by putting in the work. So 300 and above, yeah, we'll have a 30K. All right, so let's continue. Now, total momentum.
So wait, so I have a question.
Okay.
Sir, if somebody should get 350, another person gets 300, two of them will get the same 30K.
Yeah, what will happen? Let the person get the 350 first, then we'll know what to do. Okay, let's do it this way. 350 down should have 50K. Then 300 to 350 have 30K. Yeah, I think that's better, right, Paul?
350 up.
Yeah,
That
350
would
up.
be
Yeah. All right, makes sense. So let's walk in and get this done. Yeah. And the person will also be featured on our website as well, and our social media pages as well. All the best, guys. All right. So why total momentum before collision, right? Is going to be what? M1, pay attention, M1, U1, right, plus M2, U2 for two objects, right? So what these are equation number one. So I'm going to bring them all together. Okay, let me not call it any equation, right? Know that U1 is initial velocity of object one. That's the first object. Is that okay? Now U2 is initial velocity. That's before the collision. Is that okay? Of object 2. Then you know that M1 is equal to, believe in yourself. What is very possible, guys. Please. I just did that to add extra motivation to tell you how much I care about you guys. Okay. So this is the mass of, aside the money, just think about the prestige. Think about how excited you're going to be. Even as you're walking on the road, you'll be like, this guy should ask me my jam score now. If you see parents in your church, you'll be like, they should ask me my jam score. You are praying that they should ask you. But there's this score you're going to get. Anyway, you see people, you'll be dodging them.
If it's there, you use your man and bring the topic.
Exactly. So there's a score you're going to get. Anyway, I want to bring up that matter because you did very well. But there's a score you're going to have. When they start talking about jam score, your heart will start beating. May they not ask me. So this is mass of object 1. And then this is mass of object 2. So guys, extra push, guys. All right. So this is what this one has to do with what? Your momentum total momentum before collision. So let's look at total momentum after collision. Are we still together, guys? All right. Let's see. So it's going to be M1 V1 plus M2. So as we're using the same M so that it will be consistent. Is that okay? Benita, seems your network is a bit bad. That's why I keep saying, vote me as president. You will see that the educational sector will take a new turn, right? A lot of things is going to change. Free internet for everybody. But then if you post rubbish, they collect your network and your phone. All right. So remember that your V1 will be called to initial final velocity after collision. Final velocity of objects. Object 1. Then you have your V2 is the final velocity of object 2. That's after collision. All right. So that said, we can now bring everything together. You're going to have M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. So that's the formula behind the law of conservation of momentum, and we're going to be making use of that a lot. Is that okay? Okay. So now let's go over to collisions now. Let's go over to collisions. There are different kinds of collisions, right? And remember that for momentum to hold, for this law to hold, there should be the force is English. External force should be zero. Like no force should be acting on that very system for the law of conservation of momentum to hold. So take note, no external force acting on the system, right? Now let's look at the types of collision. For us to talk about collision, we must look at two key variables in collision, right? Now, two key variables must be paid attention to when I'm talking about collisions. So in collision, it is defined by two variables. What are those variables? It is defined by two variables. The first variable is defined by momentum and is defined by kinetic energy. Right? So these two variables are the physical quantities that describe collision. That defines what? Collision. Now, despite the type of, there are different kinds of collision, but in all of this type of collision, this guy is always constant. Momentum does not change, no matter the kind of collision. Is that okay? No matter the kind of what collision, this our brother here, it doesn't change. Momentum does not change, right? But these two variables define or determine the kind of variables that the kind of collisions that we have. Momentum will not change, right? It remains the same despite the kind of collision, right? So we have different types of collisions. In the different types of collisions, we have the elastic collision, we have the inelastic collision, and we have perfectly inelastic collision. Is that okay? So now, under the types of collision, we have three key types. The first one, we have the elastic collision. The second one, we have inelastic collision. And then the last one, we have perfectly inelastic collision. Are we all together? Lillian, are you there? A thumbs up if you're here in class. Yeah. Benita, is it going? A thumbs up as well if it's going well, Benita. A thumbs up, Benita, if it's going well. And I like calling you guys by name to be sure that everybody is really, really following. All right. Okay, so let's go. First one, let's talk about elastic collision. You see, elastic collision is the one that when they come together, they still separate. Example, if we throw a ball on a wall, it hits the wall and it goes off. Is that not so? So that kind of collision is what we regard as the elastic collision. There is no deformation. There's no permanent deformation, right? Everybody maintains their own velocity and then they leave. Are we together now? That is what we regard as your what? Elastic what? Collision. Nothing changes right there, right? They collide and everybody goes its way. That is your elastic collision. So for this very guy, remember I said something about the two key variables that defines our collision, which is momentum and kinetic energy. So for elastic collision, always momentum is conserved and also kinetic energy is also conserved. But you see this guy at the center, momentum is conserved as always, but kinetic energy is not conserved. Because in this very one, elastic collision, the objects will collide and everything will separate. They go back when they collide. Give me a thumbs up if you get what I'm saying now. They collide and they return back after their collision. Yes, they collide and they return back after their collision. Now, for the second one, they collide, but there is deformation. Like there can be some changes when they collide. Example now, let's say I finally buy this Volkswagen I'm walking towards. It doesn't have engine anyway. Maybe they say when I buy the vehicle, I can now go and check for engine that I'll put inside of it. So when I finally buy that Volkswagen, and then the Volkswagen comes in contact with a very clean car. Let's say it comes in contact with a Land Cruiser Prado, right? What will happen? That cruiser will not survive it because the collision is between a vehicle and weapon. So the Volkswagen is a weapon, not a car. At this moment, it's not a vehicle at this moment. So imagine a collision between a weapon. There are someone will tell you that there are some vehicle that will jam you, right? You know that there's no need taking you to the hospital. The face of the car alone determines whether you survive or not. So imagine those two vehicles now. One is a weapon, one is a normal car. When they collide, what happens? You expect the other one to be deformed. So that kind of, Dauda is here. So that kind of collision is what we regard as what? Inelastic, because there is deformation. And kinetic energy is not conserved because part of the kinetic energy will be converted into heat. Some of them will be converted into sound, right? Some of them will be converted into internal energy. So for inelastic collision, it is not what? Conserved. Momentum is not, kinetic energy is not conserved. Now, this one, perfectly inelastic. Momentum is conserved as well. Kinetic energy is not conserved, just like this one. But difference between this guy and this one is that in as much as they collided and there was deformation, right? But for this one, they will stick together. Have you seen that kind of accident before? When a car plunges into another one and the car sticks inside here, right? So that's what happens here. So when they stick together, then both of them now moves with the same velocity. That is what we regard as what? Inelastic collision for this one. Perfectly inelastic. They stick together. So once they're sticking together, you're talking about perfectly inelastic. In terms of if you understand what I'm saying. Good. So for these guys, thank you guys. Thank you. I love you all. As I know get love, make I they love my students now. Till that time. I will not be so. Nobody's saying anything. All right. So here, momentum conserved. Momentum is conserved. Also, here as well, kinetic energy conserved. That is for elastic collision, right? So if I'm to actually build on some of them, so let's build on elastic collision, sorry. Let's build on it. So for elastic collision, let's build on it. So I've said that momentum is conserved, right? For that very one, for inelastic, and it requires that they separate after collision and everybody will go their way after that very collision. So nobody sticks to each other. They just collide and everybody goes its own way right there. All right. So now, the key things about this, like I said, since momentum is conserved for that very guy, let's look at the formula for or your normal elastic collision. That's the same formula I'll be using all this while. Nothing has changed for your elastic and inelastic collision. Nothing has changed. So for this one, it is a kind of collision where momentum is conserved, right? So let me just make a little statement. An elastic collision, I seriously need to solve questions today. An elastic collision is a collision where momentum and total kinetic energy is conserved. All right. So what does that mean? That means no kinetic energy is what? Is lost, right? That means no kinetic energy. Mass people, are you sure I can still teach mass today? No kinetic energy. Mass people, no kinetic energy is lost during the collision. Now, there's something I said about this inelastic collision that they do what? That they rebound, right? Everybody will return to their original position, right? Everybody goes back, right? After that collision. That's what makes it what? Elastic. All right. So note that objects bounce off each other without permanent deformation. All right, so momentum conserved. So remember the formulas. So one, we'll have momentum conserved, m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. Then second one, 1 over 2 m1 u1 plus 1 over 2 m2 u2 is equal to 1 over 2 m1 v1 squared. Sorry, this is squared, this is squared, this is squared, plus 1 over 2 m2 v2 squared. Right. Remember, this is u. Okay, this is v rather. Remember that this one is for momentum. This one is for kinetic energy. All right. So that's for elastic collision. All good now, right? All clear. Everybody. All right. So the next one, let's look at inelastic now. For inelastic, so here momentum is conserved as always, but kinetic energy is not conserved, right? So for here, what are the key things I want you to remember for your inelastic? Number one, here momentum is conserved while, are we there? Kinetic energy is not conserved. Kinetic energy is not conserved. So what again do I want you to know? I want you to know that some of that kinetic energy is converted into heat, right? So some kinetic energy is converted because of that deformation that happens, is converted into other forms of energy. Converted into other forms of energy. Energy like what? Energy like you can have it converted to heat, sound, etc. All right. And physically, the object is deformed. Is that okay? So the third one, I should write that so that you could take note of that. Physically, comma, the object is deformed. So there is a deformation in that. Okay, guys. Okay, guys. So kinetic energy converted, physically deformed. That is for your inelastic collision. So right. So so sometimes the object might not stick together actually in an inelastic collision. Sometimes they might not stick together, but just know that it is deformed and that energy is lost and converted. So kinetic energy is not deformed, is not conserved in that very one. Now, for perfectly inelastic, perfectly inelastic is the one that is quite interesting because they stick together, right? So for perfectly inelastic, then we go to problem solving. So this occurs when the object sticks together, right? The object sticks together, right? Comma, and they move. All right. So what we'll have here, we'll have M1 U1 plus M2 U2 will now be equal to, take note, M1 plus M2 multiplied by V. So this happens when they do what? They stick together. So once they stick together, that's exactly what happens. The formula changes to this. So anytime you are solving a equation and they say that this thing sticks together, this is the formula you're going to use for inelastic collision in particular. Objects will stick together. This is the formula we're going to have. So V is the common velocity that they move together with. Everybody, does it make sense now? That's the common velocity they move with, right? Do you understand what I just said? Is that only justice, Lillian? Okay. All right. So let's quickly review once again. I want to number the equation so it will be easier for you to, so in case you're asking me a question, I know what you're talking about. So this is equation 2, equation 3. This is equation 4. This is equation 5. So equation 5, this is kinetic energy, right? Then this is equation 6 at the point where they stick together. That's what happens to the question there. And they always ask you the question of sticking together. Is that okay? Right. So kinetic energy is still the same thing, that same value, right? But for inelastic collision, the kinetic energy might not be the same. They might not be equal, right? It's expected that kinetic energy before should be greater than kinetic energy after. Is that okay? That is for inelastic collision. So it is important to note that total before, that total kinetic, total KE before collision for this very one should be greater than, right, total KE before after collision. When does this one happen? This one happens when? For inelastic collision. Is that okay? This is for inelastic collision. But for elastic collision, they are equal. Is that also? For elastic collision, both of them are equal. So that said, let me quickly look at something on bullets, recoil of a gun, how you can tackle that, and we start solving question. Hey, guys, I'm tired. Yeah, but I can't be tired, right? Yeah, I can't be tired. Nikki Gold Silver, are you here? Or she has gone to do house chores like she said the other time. As I manage. Yeah, we are in this together, bro. We are not giving up. We are not giving up, bro. Meso seems your Nikki Gold has gone to handle some things at home. All right, so let's look at the recoil of a gun. They ask this question a lot, and your textbook, you had a session for it, right? So let's quickly look at that. So for the recoil of a gun, I've explained this thing yesterday, but I want to give you the formula, right? So recoil of a gun. Remember what I said the last time? There's a, as you are trying to pull, the bullet is moving from the gun, right? As it's moving up, is giving that gun the backward movement. Is that also? So this happens because momentum must be what? Conserved. Is that okay? So for your bullets, for the recoil of a gun, right? It is the same thing I explained yesterday. So bullet goes forward, gun moves backward, right? In terms of that, right? So what happens? Total and before. So what is going to happen? Total momentum. How will I put this? Let me just go straight to the point. I've explained the recoil of a gun before. So for that one, law of conservation of momentum. Holds as well as seen earlier in Newton's third law. Are we there now? So we have the forward movement of the bullets equal the backward. That's why people like Meso cannot go and enter that she wants to enter into military now, because she doesn't have much weight. Even the gun will throw her away. So backward but that's the fact now. I've not seen all of you physically, but I can tell who is who, right? I can tell. But this that Nikki Gold from the name looks like someone that will be very heavy. her kind might be making use of a machine gun. She'll be making use of a machine gun, that particular one. It's very possible. And that person is Dauda. Dauda. The way the name sounds a lot will tell you that she's a very powerful woman. So that's the backward movement. But for Titi and the Meso, that one is very obvious. Titi, I have a question for you. When you want to shout for your child tomorrow, is that the voice? Stop doing that thing. Is that what you be saying?
No. I'll be like,
Eh?
I shall say it. When we get to the bridge, we'll cross it.
All right. I'm just asking actually to know if that's how you be shouting, how you handle the kids when they do something. But I don't believe that's the voice you use when someone eventually eats your food at home. I don't think so.
No, that's not the voice I use because
That's
they
not the
won't.
voice, right? It will not be deep. It will not be as deep as that of justice.
No. It will be loud, very loud.
Justice, my bro. I'm very sorry, sir. Ferrami, are you on this call? Ferrami, are you on this call? Yeah, Ferrami is one person that know that the children are going to mess up because her voice alone, her voice alone it sounds like this speaker that DJ people they normally use, like that has 4 outlets. Ferrami, give me a thumbs up if you are there with me, Jare. Ferrami. Yeah, you're doing a lot actually. Well, maybe we'll give you the shouting minister of shouting affairs. All right. So let's proceed. Let's go back to. Yeah, I'm just trying to warm us up a bit. I'm just trying to warm. I know that some of us are tired, so let me just warm you guys up a bit. Then we'll proceed. It's a very good one actually. Shout out to all the ladies in the house. It's not easy, right? They are the future moms and how will I put it? They'll be taking care of people soon. Yeah. Shout out to them. They're doing well. Yeah. Shout out to you guys. Makes sense. But do well. Ensure that your damn score is the one that you can show your child tomorrow. Don't go and hide it. Before the kids they want to do clean up, and they open the drawer and be seeing some kind of things they don't need to see. The best guys. All right, so for that, for your bullets, we are back to class again. So I should be like, yeah, you're doing well actually. I'm rooting for you. So you're going to have MV out there, guys. So now the formula for that is going to be MB. Yeah, we'll play and we'll still come back to class, okay? And then we'll have MG and then we'll have VG right here. So now forward movement of the bullet is equal to backward movement of the bullet. So that implies that we are going to have, this is the very formula that we use for the recoil of a gun, right? And this will be my equation number 7 at the moment, right? And remember, we can table them, right? Let's have where MB is equal to the mass of the bullet. So anytime you hear recoil of a gun and bullet, please run to this formula. Mass of the bullet, then you have VB. You should have the bullet mass of the velocity of the bullet, right? Velocity of the bullet. You have mg, that's the mass of the gun. Then you have vg. That's the recoil. I just remembered something now. recoil velocity. You can put this down. I remembered something. Back in my school, the church we attended in school, um, it's kind of open, right? It's kind of open. And that very day, the person that was preaching was talking about Psalms, right? I think he was talking about um, he that dwells in the secret place of the Most High shall abide under the shadow of the Almighty. He was trying to explain that very passage. Why I say this is because of this gun I wrote now. So the young man was saying a lot of things that we shouldn't be afraid, that we have God with us. That was the passage he was teaching that day, right? Then all of a sudden, we had the sound of bullets, and people were running because our church was open. Like people ran past the church. Even the guy that was preaching, that was standing on the altar, also ran alongside with everybody that was running. Like, oh, everyone just ran away from the church. Like that's the day. So I just remember this gun. And that was the person that was preaching about we should not be afraid. The funny thing, one thing that actually shocked me that is that he was actually talking about fear, like we not being afraid that God is with us, that some of us cannot even sleep alone at night. And that didn't happen. Baba leave pulpit run. Oh my god. Sir?
No, it's not because God said not be afraid. Me, stay there.
All right, guys. So that's the key things I will need for a coil of a gun. All right, so let's get our hands dirty. All right. So I have some questions right here that we can get our hands dirty. Everybody, hope we are good and hope you're not feeling sleepy. Right. Hope you're not feeling sleepy, everybody. We are active, I believe. Okay. Justice, you are too good. What's his name? What's the name of my bro? That's Paul. Paul, you did a very nice job. I'm seeing what you gave me here. It's very good. All right, so let's have an example now. Sample calculations. So now, this one says that a ball of mass, are we there now? So the first question, it says that a ball of mass, I wish I can import this very one now, so it makes the work easier for us. Sorry, let me quickly import it, okay? Just a few minutes, guys. Let me quickly do that so we can start solving. So review everything we've done so far as I begin to solve. All right. Yeah, Paul did a very nice job here. It's commendable. Well done, Paul. All right. Okay. Yeah, so let me quickly import it now so that we can start work. Okay. Dawood, are you still on the call? Yeah, Paul, they're asking you, where are you getting those questions? I think he sent that on the group chat. All right, so let's get started now. Can you see my screen? All right. So let's look at our sample calculation. Look at that question. It says that the momentum of a car moving at a constant speed in a circular track. Who can answer that question number? The first one there. When they're moving in a circular track.
Sir,
Yeah, go ahead. Anybody? The momentum of a car. Just send your answers in the chat. Let me pick the correct one.
sir, can you increase the picture again?
Ah. Is it okay now?
Yeah.
Okay. So momentum of a car moving at a constant speed in a circular track. What happens? Anybody? Someone say not clear. No, I'm talking about number 4. Look at the one I'm talking about. The momentum of a car moving at constant speed in a circular track. What happens to it in a circular track? That's my problem with people. You guys are saying you are following. When it comes to question, nobody can answer. A. Okay. Justice said A. Any other person? B or C. Okay. Mr. Maggie, what's your answer? Confidence said C. Okay. Mr. Ma said A. Ferrami said C. Okay. Ferrami said C. It's very funny you guys are giving me that kind of answers. Now, they said momentum of a car moving at a constant speed in a circular track. What happens in a circular track? Even if the speed is constant, there's something I said happens in a circular track. The direction is changing. In a circular track, direction is changing. And if the direction is changing, it means that velocity is changing as well. Is that not so? Sorry. Thank you. Now, so what happens? Remember that there's a statement I made earlier inside your notes here. I had to do that consciously. I had to do that consciously, right? Where I said that, look at this. If velocity changes, momentum changes. Look at where I said it here. If velocity changes, momentum will change. And what causes velocity to change? Once direction is changing, it means that velocity is changing as well, right? So which means that it can be positive and it can be negative. Thank you so much, Justice, because I told you guys that momentum is a vector quantity. Because it's vector, it can be positive or negative depending on the direction. And as you're moving around a circular track, your direction is changing. Direction is changing. And as direction is changing, velocity is changing. And changing velocity equals changing what? Momentum. So the answer is going to be what? A. Does it make sense? The thumbs up if you got what I said now. In a circular track, direction is changing at every point in time. In a circular track, direction is changing. Even if the speed is constant, the direction is changing. And because direction is changing, velocity is changing. And if velocity is changing, momentum is changing because momentum depends on velocity. And momentum is a vector quantity. Because it's a vector quantity, the sign can change depending on the direction it is moving to. Now, the next question here, as you can see on the screen, it says that a mass 0.5 moving at 10 meters per second, right? So they're giving us key details about this very object. So what are the details that we have about that very ball? Now, the first one, they gave us M1. So M1 is equal to 0.5. Moving at 10 meters per second, U1 is equal to 10. Collides with another ball of equal mass. That means equal mass also means that M2 is 0.5. If the balls move together, these statements move together tells you something. It tells you that it's an inelastic collision and that they stick together. So if they move together after the impact, calculate their common velocity. So which formula do we normally use to calculate the common velocity? Now, you've looked at the question already, so I just want to bring out the data that we have. So we have M1 is equal what? M1 is 0.5. We have M2 is also equal to 0.5. U1 is equal to a body of mass 0.5 moving with 10 meters per second, collide with a number of equal mass at rest. So now this is 10 meters per second, but U2 is at rest. That means it's equal to 0. So it means that since you are looking for common velocity, V, we don't know. You know, this is an inelastic problem. This is an inelastic problem, perfectly inelastic problem. So we're going to have M1 U1 plus M2 U2 is equal to what? M1 plus M2 V. U1 is 0.5 times 10 plus M2 is 0.5 is at rest, which is 0, is equal to 0.5 plus 0.5 multiplied by V. So now 0.5 times 10 is going to give me 5 here, plus, okay, that's 0 already. 5 here is equal to 0.5. This will give us 1V, right? So it means that V is equal to 5 meters per second. So it means that we have the answer here. So our answer is going to be what? C. All right. Everybody, all clear, right? Good. Look at this one. This one says that a body is moving at 4 meters per second if the impulse after accelerating at 5 meters per second for 2 seconds is this. So they're giving us our impulse. Remember that impulse Ft is equal to what? mv minus u, right? So they said a body moving initially at this, if its impulse after accelerating this, what is the mass? So now they've given us key things. They gave us our u to be equal to 4 meters per second. They gave us our ft equal to 60. They gave us our time to be equal to 2 seconds. What again? A is equal to 5. They asked us to find our m. Now, what do we know? So look at how we're going to solve that very problem. You know that impulse is equal to force times time. Impulse is 60. We don't know the force. They gave us the time. The time there is 2 seconds. That is 2. So it means that the 60 is equal to 2F. Divide both side by 2. Divide both side by 2. You have that F is equal to 30 Newton. But recall that F equal MA. We are looking for that mass. Now, the value of your F is 30 is equal to mass times acceleration was given us as 5. So 30 is equal to 5m. Divide both side by 5. Divide both side by 5. You see that m is equal to 6 kg. Any question on that? Any question on that? So it means that this very question, that the answer is 6 kg. A thumbs up if you're following now. All right. So let's go over to the next one. This one said a lead bullet of mass 0.05. What if you use Ft equal to Ma directly? Yes, you can. That's a nice one. You can apply your second law. I just have to break it down. Yes, you can, of course. You can do this. Of course, you can. We have that F is equal to mv minus u all over T. Is that not so? You can actually. So you have Ft is equal to, but what happens? I don't think that's a good approach actually, because you cannot, this whole of here will give you acceleration. You don't know the force. Do you get, Emmanuel? Do you get the point? I don't think that will give you a better solution. Yeah, you cannot, because you don't know the force. You have to calculate the force first. All right, so look at this one. A lead bullet of mass, 0.05 kg is fired with a velocity of 200 meters per second into a block of mass 0.95 kg. Now, if it is fired into a block of mass, it means that the block is not moving. Is that not so? Given that the lead block can move freely, right, the final kinetic energy after the impact is what they asked us to find at this point. All right, so if it's fired into the block and they said that the block can move freely, that's another statement, right? That's another statement. All right, so that said, let me quickly check something right away. All right, let's proceed. So a lead of mass, I've given this already. We have this mass is fired with a velocity of this. Good. That's before the collision into a block of mass. This, given a lead block can move freely, the final kinetic after the impact. So it's assumed that the bullet is going to stick inside the block. That's my assumption. That after that, when it enters that block, it's going to stick there, and all of them are going to move together, since that block can move freely. Do you understand what I'm saying? Good. The sisters in the house, Lily, Titi, Meme, Titi, Meme. Okay, who again is there? I think Susan is here. Okay, Susan is not here. Ferrami, Benita, Bebe, Abi. That's how they call you guys at home. All right, so let's have that. So it's assumed that they are going to move with common velocity, right? That's what I'm assuming, right? So we have our M1. But I think that's the name they call you guys at home. Is that not so? You know how you guys can be. Once they call you guys that name, you feel good. They are giving me a thumbs up or thumbs down. Okay. Do they call you Antanekereja? So we have that M.
Sir, if they call you with that, I know that they're about to send you an error.
So M1 is 0.05. Please, you understand the logic I'm playing here, right? That if it is fired into a block, it's assumed that the initial velocity of that block is 0. But once that bullet enters the block, since the block can move, because of the force that the bullet uses to enter the block, it will move with the block. It will stick inside the block and move along with the block. Do you get? Yeah. So that implies that M1 is 0.05. Then we'll have that U1, that's initial velocity of the bullet, is 200. Now, M1, M2, mass of the block is 0.95. Then U2, we assume that the block is not moving initially. But after the collision, no, this is before collision. Is that also? Then after the collision, we assume that they now stick together, right? And they have a common velocity. V is what we are looking for, right? We look for common velocity, and then kinetic energy after the impact is also what we seek for. Everybody, thumbs up. Everybody, thumbs if you're following. Yeah, Benita, you're there? I want to be sure Benita is following. Okay. All right. Who again? For the guys, I think we are all good. All right. My guys are good. Now, before collision, I think it will be fine after jam. We'll have a get together. How do we achieve that? How do we even achieve that? They are giving me thumbs up. If you visit in a place that is not your location, will you come? They are giving me thumbs up. So before collision, we'll have distance is a barrier actually.
Let's see our score first.
Exactly. The score would determine where the score would determine whether it will hold or not. So we have M1 is equal to before collision 0. This guy is very funny. Yeah. So we have U1. I've written them down. That's 200. Then M2 equal to 0.95. That's for the block. U2 is equal to 0. Right. Then after collision, they stick together. Is that also? They stick together. So we'll have V, which is unknown. So let's bring them together. Remember that this one is for the bullets, please. Bracket for bullets. This is for bullets. This is for the block. This is for the block. So that when you are reading, you can always remember. So we'll have, let's put it together. M1 U1 plus M2 U2 is equal to M1 plus M2 multiplied by V. So this is 0.05 multiplied by 200 plus 0.95 multiplied by 0 is equal to M1 U1. That's 0.05 plus 200 V. Remember, it's not V they asked us to find, though. They're supposed to find the final kinetic energy, but we need that velocity to get the final kinetic energy. So now let's quickly multiply. This times this should give us, this side is 0 already, so this will give me 10 here, right? Is equal to multiply, add this side together. So I'm making a mistake with this M2. I'm using 200 here instead of 0.95. So what's the value? Anybody adding it together? That will give us 1. Yeah, 0.95 plus 0.01. Yeah. So that will give us 1 V, right? So that V is equal to 10 meter per second. Now recall that kinetic energy will now be equal to 1 over 2 m. We are going to put their mass together, right? M V squared, right? But M will be equal to M1 plus M2. And V is our final velocity. Is the common velocity, actually. Common velocity. So that the kinetic energy will be equal to 1 over 2 times by, the M is what? 0.95 plus 0.05 multiplied by 10. Are we following? So we have the kinetic energy will be equal to 2 here is 1, here is 5. So I'm going to have, this is 1 here, so this is 1 multiplied by 5. So kinetic energy will be equal to 5, sorry, will be equal to 5. Yeah, who is that person? Am I making a mistake at all here? Mute yourself now. Sorry, this is 10 squared here. So mute yourself. Who is the person? Mute yourself, please. This is times 10 squared, actually. Yeah, 10 squared. That's 10 times 10. So if I cancel one of them, to here. Here will give me 5. So that means we'll have 50 right here times 50. So that will give us 50 joule. All right, so we've solved that very problem. So which means that the answer is going to be 50. All right, so the next one is the one from my pro. All those questions that I sent on the group chat is very, very good. Like very amazing questions that if you read them, you're going to do well. Are we together? So let's look at this one. So let me zoom on it so that we can see. They said a bullet is fired at wooden block of thickness 0.5 meter, manages a bullet fired at a wooden block of thickness 0.15 meter, manages to penetrate the block, right? If the mass of the bullet is 0.025 kilogram and the average resistive force, are you there? Average resistive force of the wood, if you know the average resistive force of the wood, and they said that the average resistive force of the wood is 7.25 times 10 power minus 3. They said calculate the speed of the bullet just before it hit the wooden block. Did you see that? What are we calculating? We are asked to calculate what? The speed of the bullet just before it hits the wood. Now, take note of key variables they gave us here. Don't be confused. They gave us the thickness of the wood, and they said that that bullet manages to penetrate that block, right? And the mass of the bullet, this is the mass of the bullet, and the average resistive force. That means the force. Can you see the question? So that's the force. The force the block is using to resist it from penetrating is 7.5 times 10 to the power of minus 3. They say we should now calculate the speed of the bullet just before it enters, it hits the block, right? So we have to make use of the thickness, right, which is 0.15. We make use of the mass of that body. They will make use of the resistive force. Now, remember that when the speed of just before it hits it, just before, what happens when that bullet hit that wooden block? When it penetrates, the final velocity is 0. Is that also? The bullet is going to stop. The bullet is going to what? Stop, right? Now, do you know what I'm going to use here? It's a bit different from your momentum here. Like the question is a bit different from momentum, but it's not something that we cannot solve basically. So look at what I'm going to do now. Now, the distance given is 0.15. That's the thickness. The mass of the bullet M is 0.025. The force is 7.5 times 10 raised to power 3. The speed you're asking me, final velocity V, will be equal to 0 because that body is going to stop. Now, this is a topic we call work energy principle. Actually, it's different from, it's not the same thing as what we did. Well, just take note. We're going to have that work done is equal to change in kinetic energy. Remember that work done is force times distance is equal to half mv squared. Are we there? Not mv squared at this point. We're going to use squared because final velocity is 0. Use squared because they gave me the value of u is what I'm looking for. Are we together now? Are we together? It's a bit different from, it's not really related, but then you have that concept. So the force that was given to us was 7.5 times 10 to the power of 3 multiplied by the distance was what again? 0.15 is equal to 1/2 times. They gave us the mass. The mass was 0.025. So this is 0.025 multiplied by what we are looking for, u squared. So now, quickly, our calculator now, let me get mine. Because the number is big a bit. So I have 7.5, which is simply at 7,500 7,500 multiplied by 0.15, that will give me 112, right? So here is 1125 is equal to 0.025 divided by 2. That will give us 0.0125 u squared. Since I'm looking for u, what will I do? I will take square root of both sides. So we'll have that. Sorry, first of all, let me divide both sides first. So I'm going to divide here by 0.0125, divide here by 0.0125. So that my u is going to be the what? The square root of what? 1125. Are we there? All over what? 0.0125. So that will give me the square root now. Square root will give me 1125. 1125 divided by 0.0125. And that will give me 300. So that u is equal to 300. Are we together? Remember, it's going to be 300 meters per second. Any question on that? Any question on that? Any question on that? If there's no question, give me a thumbs up if we're all together. Yeah, good. Good. So remember that what I used here for this very question is a bit different from what we're doing, but it's still the same concept. So I used work done, right? That's the formula I applied here. I used work done is equal to change in kinetic energy. By now, you know what work done is now, right? Work done is force times distance, which is equal to 1/2 mu squared, right? So I just plugged in my equation, 7,005 times 0.15 equal to 1/2. I'm doing this because it's a bit tiny on the paper. For some of us that have Drangari so much that if we see white, it looks like black. So we have confidence. Since you drink a lot of Gary, the way you are laughing, the thing just sweet you, eh? It just brought back memories for you. Take it easy. Take it easy so that somebody's you know, you are somebody's wife. So the husband will have a wife that has eyes. Because take it easy. So this will cancel this. So that u squared 125 all over 0.0125. All right. So far, so good, right, guys? So u equal to 300 meters per second. So far, so good, right? All right. So next one. Okay. So this one says a ball of mass 0.5 kg is kicked against Benita, are you following? Justice Ezechinon. So Lily, are you following? Maybe and the rest of them. I hope you guys are following. Ferrami, hope you are following as well. Yeah, you know, we've entered problem solving now. Yeah. So a ball of mass 0.1 kg, 0.15 is kicked against a rigid vertical wall with a horizontal velocity of 50 meters per second. If it rebounds with the horizontal velocity of 30 meters per second, calculate the impulse of the ball on the wall. Now, you know the wall is not moving. Is that also? The wall is not moving. That's one thing you have to know. So initial velocity of the wall, 0. Final velocity of the wall, 0. Is that also? The wall is not moving. Look at the statements here. Give me a thumbs up now if you understand what I'm saying. They said it is rigid. That's the statement here. So because of the fact that it's rigid, the wall is not moving. So final velocity of the wall, 0. Initial velocity of the wall, 0. It is not moving, right? So that's established. We have that the ball M1, which is the mass of the ball, is equal to what? Mass of ball is equal to 0.15 kg. Now, the next thing they gave us is horizontal velocity, which is 50 meters per second, right? Before it hits the wall, right? So remember that this part of things is my before collision. Before collision. Now, mass of the ball is M1 against a vertical rigid wall. Do I even need this? Do I even need collision? I don't need collision, brethren. I don't need collision. I'm just looking at that. Remember that impulse equal momentum. Is that not so? Now, you have that mass of ball, because the wall is rigid. Mass of ball is 0.15. Initial velocity of ball. Do you know? Have you seen why I changed that very formula? Because there's nothing I'm going to do there, because they're asking for impulse. I just look at this impulse they are looking for, so there's no need. So final velocity and change the momentum is equal to impulse. Final velocity of ball will give me what? 30 meters per second, since it rebounds back. So now, based on that, we have that impulse is equal to mv minus u. So that the impulse is equal to 0.15, open bracket, if it rebounds with a horizontal velocity of 30, right? Now, direction should come into place. So if I play you against positive, you are going back negative. Are we together? Direction, that's what I taught you before. Momentum, yeah. So let's assume that when he hits the ball, this is positive. Yeah. Please pay attention. Yeah. Direction matters, because momentum. Why are you laughing? Is it because I'm saying yeah? Don't worry. I'm going for phonetics class very soon, okay? You've got to wait for me, right? You got to wait for me, right? Good. So now, final velocity. I'm not a Nigerian. Is it because Igbo has dealt with me that my English now, eh? Oh, my God. All right, so let's proceed. So you have plus minus. Do you know why you have that sign? Let's say this is the wall. Let's have this as the wall. Direction matters a lot. Let's have this as the wall. Now, when it hits the wall this way, the direction are different. So hit, rebounds. Are you seeing it now? So anyone that works for you, you can change the sign depending on the sign convention you want to use, right? Hit and rebounds. So now that implies that final velocity is we'll have minus 30, then minus but wait, the sign should be, if it's going to the left, I told you left is positive, Abby. Is that what I said? Left is positive. Was that what I said? A thumbs up. Check the convention we are using. Can someone quickly check the convention I agreed we are using? You are giving me thumbs up. How will I know the thumbs up? Is it a thumbs up that left is positive or negative? You guys can confuse somebody in this life. The thumbs up, is it which one? Paul, I think we can use any convention actually, whether left or right. Whether you go left, let's say right is positive. Okay, let's use left to be negative. So that as he hits the ball, we have a negative 50. As it bounces back, we have a positive 50. So with that, now we have Okay, I have a negative 50 and a positive 50. Now, what I'm looking at, we have to check so we don't end up with a negative sign for our impulse. Is that okay? That's what I'm trying to ensure that it doesn't happen, right? So let me check again. So if I hit my wall, left hand side, oh boy, negative. So I have V, initial velocity is going to be plus negative 50. Negative is going to give me positive. Yeah. So let's go that way. Are we together now? Are we together? So what I'm going to do, let's invert the sign. So we'll end up with a positive sign actually, right? Anyone that I want to do is entirely fine. So let's go this way. Let's have the heat to be negative. It's going to the negative direction. And let's have the rebound to be positive, right? So the heat, initial velocity is going to be negative. Let's just apply that. Now, the final velocity is going to be positive, just indicating change of sign. Any sign convention you want to use, at most you take you know what we call absolute, you take the absolute value. That's the magnitude. Anybody that knows that, you can take the magnitude. Anyone at all, it's still the same answer. So I have the initial velocity here minus, this is 30 actually. This is 30 actually. Final velocity, initial velocity is, this is 30 minus final velocity minus 50. So that the impulse will be equal to 0.15, 30 plus 50. So that the impulse is equal to 0.15 multiplied by 80. So any sign convention, even when it gives a negative sign, you just take the absolute value. The magnitude is what you're looking for, right? Is that not what they asked us? Calculate the impulse, yeah. So impulse will now be equal to 0.15 times by 80. Math people, sorry, forgive me. I'll find a way to do that class tomorrow for you. So this will give us 12 Newton seconds. Everybody, any question on this? Any question on this? Remember that momentum is what? Is vector quantity. So we have to indicate the sign. Any question on this? If it gives you a negative, if you use it the other way around, just take the, if you use the other way around, just take the absolute value. Look at what I mean. Let's assume somebody wants to take the other way around. Are we together? Let's assume somebody wants to do it the other way around. Someone who might tell me, what if the block is like this? Let's assume the wall is not here, but the wall is facing this direction. Anyone you want to use is entirely fine. That's what somebody can ask now. So the wall, you want to draw your own wall like this on the right-hand side. So it hits it here, right? When it hits, let's say that I'm taking heat to be positive, right direction, to the right. So let's have rebounding. Nobody's giving me a thumbs up. This is my heat. This is my rebound. Are we following at all? And let this rebound be a negative value, right? So anyone you want to do. So that means that our heat now, when you hit it, that was the initial velocity, and that will give me plus 50. The rebound is going to give me a negative 30. So that impulse will now be equal to 0.15. Open bracket, V is minus 30 minus U, which is 50. So it means that impulse, so anyone that works for you, impulse is equal to 0.15 minus 80. So impulse is equal to negative 12 Newton seconds. You take the absolute value. So impulse, take the absolute value. That's your magnitude now. Take the magnitude. So that the magnitude, so the impulse is equal to 12 Newton seconds. So what you did here was, not by, we just took the magnitude. A thumbs up now. So anyone you use the same answer. Just remember, if you have negative, remember to take the magnitude. All right. So any other question on that chart? Let me check if there's another technical one there that might require me touching it before you guys resolve. Any question? Any question? Any other one that Paul sent that was not tackled? Force of magnitude, find a particle velocity at a speed, it rebound was the impulse. Yeah, I think I've touched key things here. Must find a new velocity. Yeah, every other thing. Okay, let me quickly solve one that has to do with the recoil of a gun. Is that okay, guys? Let me quickly do that. So you see what the question looks like. Let me do that. There's a question I saw that has to do with recoil of a gun. Let me quickly do it before we call it a day. Yeah, I know I saw that question. Good. So look at it. The next one. So I've solved how many questions? 1, 2, 3, 4, 5. So let's call this question 6. So it's from that past question that Emmanuel bought for us. So number 6, a machine gun. A machine gun with a mass of 5 kg fires a 50-gram bullet at a speed of 100 meters per second. The recoil speed of the gun, the machine gun, is, they gave us options. A, can someone solve this from the formula I gave you? 0.5 meters per second. B, let's see who gets it correctly. 1.5 meters per second. C, they gave us 1 meter per second. D, they gave us 2 meters per second. And E, they gave us 4 meters per second. All right, so who is getting their hands dirty on this? Who is getting their hands dirty on this?
So C.
C. Any other person? Any other person? Is it only Paul? Is it only Paul? Paul, are you the only student in the class? Confident, Emmanuel, Justice, Ferami, Lillian, Mesop, Susan, Titulola. What's your answer for that very question for Mass of the Gun? You guys are not copying notes, that's why. You guys are not copying the notes. That's why it is that way. So now, solution. Everybody is now calm. Solution. I gave you a particular formula that I said that forward movement of the bullet equal to backward movement of the gun. So what's your answer again, Paul? We have
1 meter per second, sir.
1 meter. Okay, we have MB. It's funny that the entire students in the class, nobody's saying anything. So now MB times VB is equal to MG times VG. Now MB, mass of the bullet, VB, velocity of the bullet, MG, mass of the gun, VG, recoil velocity, speed of the machine gun, of the gun. So now they gave us the mass of the gun. A gun has a mass of, let me be detailed a bit. Mass of the bullet, right? MB, mass of bullets, mass of bullets is equal to 50 gram. 50 gram is the same thing as what? 50 times 1000 is what?
0.05.
Sorry, divided by 1000. Sorry, divide by 1000. That will give us 0.05, right? So that's 0.05 kg. Remember to convert. I converted, right? So now VB, that's the velocity of the gun. Sorry, velocity of bullets rather. Velocity of bullets is equal to what? 100 meters per second. I'm not happy at all. So the next one is MG, the mass of gun. Mass of gun is equal to, the machine gun is what? Has a mass of 5, right? So now the VG we do not know. So let's plug in the value. I have 0.05 multiplied by 100. That by 100 is equal to 5 times our VG. So which implies that 0.05 by 100, that will give us 5. Thank you so much, Paul. I'm proud of you, bro. So 5, that will give us 5 VG. Divide both sides by 5. Divide both sides by 5. You are getting 10 measure because you didn't convert. So VG is equal to 1 meter per second. Now, remember that the mass was given in, that the mass of the gun was given in, mass of the bullet was given in gram, right? So note, that mass of bullets, they gave us to be 50 grams. So 50 divided by 1000, that will give us 0.05 kg. Is that okay, everybody? Those, the rest of you in the class. Is that okay, everybody? Give me a thumbs up immediately. All right. So that's it for today's class. I wish you all the best. Always remember, just a little recap. We started with momentum, gave some introduction on momentum, and the key things about it. I gave you that it's a vector quantity. I gave you that you have to take note of the direction and the signs when solving momentum problems. I went ahead to introduce impulse. We looked at conservation of momentum and everything you need to know about conservation of momentum. I talked about the law of conservation of momentum. That's a law of conservation of momentum. So any question, guys? And then this is what we decided on that. Total momentum before collision, total momentum after collision, types of collision. We looked at elastic, inelastic, and perfectly inelastic. Elastic, both of them are conserved. inelastic collision, nothing is conserved. Inelastic collision, only momentum is conserved. The other ones are not conserved. And we solved a good number of questions of that. Recoil of a gun. And I gave you the formula for recoil of a gun, which I just used in solving the question I solved now. And we solved a lot of questions regarding what we've done so far. So I wish you all the very best, and I hope that you get to solve more questions and you get to revise your notes as well. All the best, guys. Any questions so far? Any question?
No, sir.
Okay. Okay. All right. I'll see you guys later now. Love emoji, please. Let's have that love emoji, please. Sawami with love, guys. Yep. And I hope you understand everything, not to give me love when you don't understand. Hold your love if you don't understand what I taught you. Put me in your prayer. I'm very sick. Sorry, Susan. I'm going to give you a call after now. Right? You'll be fine. 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 All right. All the best, guys. I'm sending the note to the class so that I can take it off from here. I love you all. Thank you. Titi, go and call her. We'll call her on phone and pray for her. All right. Bye, guys.